My avail- screen is visible.
Yes, ma'am.
Okay. Now let's understand. See, the first thing or the main concept that I need to make you clear is what is a difference between a classical system and quantum system or quantum computing. When you are seeing it, I suppose you might be whatever is available on internet, they all talk about in the physics term like in quantum mechanics, but we are not able to find, you are not will not be able to find. Even when I was searching, I also listened many abroad universities and many lectures, and there was no relation they were showing what is the relationship between the classical and quantum, or how we are going to deal it with. So this subject I will start from scratch. That means we will be dealing, because whatever computer subject we study, we normally deal with binary data, that is the data of 0 and 1. So now how this data is related to quantum bits, or we call them qubit. So when you are able to understand this transformation, we can do anything. Now this transformation is not so easy. Why? First of all, let's understand this. In classical computing or the classical system, we have binary data. That means the bits are 0 and 1. The information is exact, either you are in 0 or you are in 1. While in quantum, the bits we call as qubits. These qubits are not like exact data. They are, you can say, it is combination of two or more state. For example, when you are spinning a coin, in classical, the, the coin shows head or tail, that is 0 1. But in quantum, the spin information is qubit. That means we are not in exactly 0 and 1. We are in a combination. We can just say in a random, it may be 0, it may be 1. So that is. And if you are just having only one of this state, you are storing head and tail, only this thing. If you are talking about the electron, there can be many other parameters. So that is why I've written it is a combination of one or more states. So what is actually in qubit we are representing? So qubit can be represented by spin of electron or polarization of photon. So what is this concept, or what we want to talk about, this spin of electron? Let's talk about that. You might be remembering more than me because you have said it recently. So if I am wrong, then correct me. Niels Bohr and odd model. Silver atomic number 47. And if you remember, the configuration of silver is 4d5s1. Here comes. So you might remember Niels Bohr given this model, and the electron are revolving in different orbit. If they are in the same orbit, they are having the different spin in a different direction. I'm not remembering the exact terminology, like we were having spdf orbital. So if they are in pairs, what happens? The magnetic field introduced by each of the electron get cancelled. And this we all, I suppose this you also, you might remember that when an electron is revolving, an electron in motion always generate a magnetic field. This suppose you might have studied in magnetic field in a more intense manner. So only that concept we are using. So the concept is, when an electron revolve, it is generating a magnetic field. And when these electrons are in pair, the magnetic field get cancelled. But what about this last electron? Yes, its magnetic field is not cancelled, and that is why we call such substances as, I suppose, paramagnetic. So the concept was this: the outermost electron magnetic field does not get cancelled. With taking this concept, he was the first scientist which noticed it, and this experiment is very much famous in quantum computing. Just wait a minute, student. Yes, students. Okay. So Stern and Gerlich performed an experiment. What it says that single electron can spin up and spin down. And you might be remembering how are we going to find the magnetic field direction? Like if you revolve the your thing's direction, you will be getting the magnetic field direction. All the magnet behaves like a dipole. So the same concept apply here also. So electron can spin. Every electron has a magnetic behave like a magnet. That means when it is behaving like a magnet, it will be having both north and south pole inclination. It can behave like a magnet, so it behaves like a small bar magnet, if simply said. Now, the both scientists did, these both emitted silver electron and passed this electron into the bar magnets. So it was they had a source which was emitting silver atom, and then they placed bar magnets, and then these beam of light were, and there was a screen here. Now, what was assumed? The assumed was, because see, we are not having only one atom in the presence, there are multiple atoms. We always know that if we take about just 47 gram, they are having one more electron. So these are 2 10 to the power 23 electrons, such a huge number. So it was assumed that electron will get deflected by the by the repulsion force of this magnet, and we will be getting a continuous pattern on the screen. The electrons will be getting deflected and they will be hitting any direction anywhere on the screen. But what was noted in the experiment, there was just only two dots, one on the extreme north and one on the extreme south. There, the assumption was that there are 20 to the power. If I'm just taking 47 gram silver, the assumption was that the line should be, or the reflection should be anywhere. But what was seen? The electrons were deflected only in the two direction: the extreme left, north, and extreme side. And how much deflection depending on the intensity of this magnetic field. So now the question comes, what is happening? Because the concept is, we have, because now we are talking about very smaller item electron, and how can they all the electron go in one direction? So now it's clear that that if we measure the spin in vertical, none of the electrons are not having any direction. The moment the magnetic field come, they incline themselves. What is happening? When they were just revolving in the last orbit, they were not having any orientation. The moment we placed a magnetic field, they inclined towards the direction, and those were having, see, those were having north pole this side, they got on this side. Those were having south, they got this thing. Or simply those who were having south this side, they also got repelled. And that is why all the electron were either on the extreme north or extreme side. Now, this was seen. So now the question come: if we rotate these bar magnets north and south, do we get some changes? Yes. What were the changes? Again, the same. This north and south plane, they also got deflected. Are you getting my point? That means if we rotated these bar magnet by rotated by theta angle, then on this place these these positions also get deflected by these some amount of angle. Okay, so now question comes, that means something is probabilistic also and something can be determined also. So what actually? So actually the thing is, in quantum you are going to store the information in very quantum or very smaller level of particles. That is electron, not the whole, and electron movement and all. That is what we call it. So now the question comes, if we are rotating it, then also we are able to get the deflection and everything getting rotated. So how can we relate it? Okay. So before understanding it more, one more depth, I will just give you one more concept linked to it: quantum clock. Now suppose you are having a regular clock in your hand and you are not seeing it, and it is, suppose it is not like digital clock, it is an analog clock and have some hour marked on it. In a regular clock, we have a button, or simply we can judge by the clock direction. Oh, this is in which direction? And suppose I ask you, what is the timing? Is it 12 o'clock? Because you will be seeing that the dialing, that side button is available. The clock is in the correct position. You can say, oh, it is 12 or it is not 12. But now about quantum clock. Quantum clock, it is something like that. Now the thing is, there is no like a different clock where there is no marking on anything is given, and you are not allowed to see the face of the clock. Now suppose I ask you a question: is it 4 o'clock? Now you may give the answer, yes, it is 4 o'clock, but maybe you give, no, it's not 4 o'clock. Because just have a look, 4 o'clock and your one is 4 o'clock and the other timing is, if you take about 6 o'clock and 12 o'clock, they all both the orientation. Huh, and 8 o'clock, 4 o'clock and 8 o'clock. Because the face of the clock, we don't know it's on the upward side, downward side, and you are not allowed to see the clock. You are just touching it and giving the answer. It is 4 o'clock or it is 8 o'clock. So simply we cannot give the answer in a very much accuracy. So quantum is not a regular clock. If we answer cell, or we can say the hand is pointing to the exactly opposite direction. That means what I said yes, it is giving the, it's 4 o'clock, but no, because now I'm not able to see the clock. Similarly, I'm not able to see the electron. I cannot predict where the electron is going to get deflected. That is why in this the prediction becomes a bit tough one. So simply, if the hand is pointing to 4, it will be either tell us that it is pointing to 4 is related to 10. 4 is a 10. No, 4 is to 8 only. 8, yes. So simply, the concept, I suppose you might have understood. The basic is that in quantum, you cannot be deterministic. The concept of probability exists. That means you will not, like in the electron spinning, you were not sure, you were predicting that electron will be hitting anywhere, because they might be getting some deflection, lighter deflection on this screen. What happens? That all the electron, there were so many electrons, they only focused in two extreme points. So I'm not able to predict it. And just the thing is, the moment we rotate it, then also it doesn't get scattered. The whole thing get inclined in the same angle. So now a question comes, that how are we going to do measurement, or how are we going to do this calculation, or how we are going to store the information. So for this thing, I suppose quantum clock has given you an idea of that we are doing the measurement in something where we are not able to see the, like the face of the clock, where we are predicting by just guessing. Maybe we are right, maybe we are wrong, and it depends on how we are doing the measurement. Suppose, like, it was a simple clock case, so either you will be 50% right or 50% wrong. In the case when it was like 4 o'clock, or I was saying it's like 8 o'clock, so it is in the both the case, either you will be correct or you will not be correct. But when we are going in more deeper, the chances of both may increase or decrease. Understood a basic idea of what quantum get differentiated, or how is quantum getting the difference? Okay. Now there, because I'm just making you why we will be doing a different type of maths in this quantum computing. Now next comes, so this is very much clear that the answer to any question when we are doing in this quantum clock or this, it's highly unpredictable. Now question come, we perform the same measurement in same direction. That means I am using the same source, I am using the same set of magnet. Will I get the same level of deflection, or will it change? or will the intensity change? So now the question is, when the experiment was repeated, when we were having the exactly same experiment, we get the same result. That was a good, interesting part. That means if you are able to have the same pattern, you could be getting the same result, you will be getting the same intensity. So that means if I am if suppose electron, I, I will just writing it as a vertical direction, south and north pole magnet that I place, suppose I named it as vertical direction. I had the same pattern, and now I'm placing my these magnet in four different type I pattern. So I will be getting the same results every time, the same intensity in the north and poles. The experiment result got repeated. But now understand. I first place the magnets like this. Then I place in vertical and then I placed in horizontal direction. That means I place like this. I rotated with the angle of 90 degree. And then again in a vertical direction. So when I was just, first of all, let's discuss this thing. When I did this thing, first in vertical, then in horizontal. Now what is going to happen? The movement, now it's unpredictable. Electron behaving pattern is unpredictable. So simply you will be getting a different result. We are getting a different result, and the important part is no relation of second result depends on first outcome. That means it is truly random. Now, how the electron will behave, how the electron will spin, and how many electron will hit in different direction, that is totally. So what we did, we had the electron hitting on this, then I passed the electron hit it in a magnet which is in the horizontal direction. Again, I noted. Now again, I saw a different type of pattern on the screen, and that was not dependent of how much intensity was on the north side and how much was on the south side, which was not dependent. And to a surprise, if I did the same experiment with this is very much clear, first and second. Now suppose if we repeat the same one, then also the answer, or you can say result, need not be same. So the result of first and third also need not be same. Got an idea? So just see the randomness level in this. The moment something gets changed, the results are clearly getting changed in any direction. I suppose there was one very interesting, so just give you thing. Hmm. Okay. Hmm. This is here. So here gives an idea. That means if I compare measurement in quantum and classical, in classical, measurements are accurate, you are clear, and effect of environment on measurement is negligible and further can be made negligible. If you this correction and this all changes you might have studied in different courses, like the noise level impact, changing the bit pattern. So no doubt the bits, because there this that is also electric fluctuation in the classical computing we do, and that only we store in the bit form of 1 and 0. So that noise, that all pattern, we have different error correction codes, we have simply methods like parity bit check when we are doing the transportation and all. So first of all, the measurement, we can have the measurement so that the errors are very less, and further we can have the measure so that these errors are less and our data is accurate. That is the reality we are able to communicate very nicely in the classical. But in this new era where we are going to jump in quantum mechanism, you have just in my previous discussion I told you randomness come, we cannot be sure the moment the electric that magnetic net gets a little deflection. Similarly it will be the second experiment. Now if I repeat back the first experiment, it's very difficult to get the same answer. Now understand this thing. Suppose both sender and receiver are having the same mechanism of generating that qubit, but in between, a error occur. Now the what is happening? They are having the same parameters, then also they cannot get the same data. So we and now we are not dealing with just leveling one and zero that can be corrected. With one electron, you are storing multiple things, and that also in a many quantum level information. Got it? So now this is going to be totally random result. So we require some operation or something that this can be changed. This can we can get the exact same values what was time, or simple words if I say, we require an approach through which we can reduce randomness. So randomness is present in quantum mechanics, and that is why we are able to store multiple information. Our objective is to remove this or reduce this randomness. How it? Just have a look. I'll just give you more idea of that. But in quantum mechanics, sorry, we consider tiny particle like atom or electron. For the for measurement, we interact with system, but these interaction will affect the measurement. Example, magnetic field outside twist electron to align to magnetic field itself. That means you have suppose sended information with the magnetic field, but the magnetic field is present anywhere, so it can create a deflection. So whatever your information you're sending, it may get changed. So that is the reason in quantum mechanism that any particle, the problem is creating more. So what we require, so now the question come, measurement we require. Without measurement, without having the exact data, we cannot do further. And that is the reason we are studying quantum computing. We can store multiple information, but if we are not able to measure at the receiver side, if we are not able to deliver on in a perfect manner, what is the need? What is the benefit of studying this thing? So we require a proper way to communicate. We require a proper way to measure the data that we have sent. So there is one more difference in classical and quantum, and that is randomness. In classical, in classical computing, do we have a randomness? In classical computing, do we have a randomness? We have the randomness, but that randomness is not true randomness. It is actually a pseudo randomness. What does it mean? Now, suppose you might be using that random number generators and all. Normally, if we have modulus operator or if we do some multiplication, that means same operation you repeat, you get the same set of numbers. It is appearing to be a random number, but if you perform the same experiment pattern, we will get the same result or not. So such type of experiments we call as pseudo random. Similarly, sometimes you might be thinking, ma'am, that head and coil toss or dicing of sorry, we are throwing the dice. That might be a random, but that is also not actual random. That is also pseudo random. It is normally proven that if you can measure the dice dimension and if you can predict how is it spinned, we can predict it that it will be landed in zero or one. So there also the experiments and the result are that can be predictable. So actually randomness is pseudo in the classical all the word till now we are dealing. But in quantum, the randomness is real because now for these minute particles we cannot judge how they are going to behave, where they are going to spin, in which direction they are going to spin. So there are no hidden variable, no approach which can till now remove randomness. In classical, initially it was assumed. Later it was found when we repeat the experiment, when we repeat something, we are able to get the same set of result. But in quantum, this is not possible. The randomness exists. That is why it is an open field and a challenging field. Now you can understand what is the issue in this quantum. The issue is you need to send the data. For sending the data, you require the data does not get modified. The problem is that the environment condition or the hazard which is present, they may change the because we are storing the information in the magnetic and the rotation and this fields of the electron which get deflected by the environmental hazards. And if a single thing get changed, a single parameter change, exactly if you repeat the same experiment at the receiver side, you will not get the data. So that error, it's the error correction is going to be a challenge thing condition. And further, the whatever are the experiment, they are totally random. So now the next concept come how we are going to use this randomness and this as our approach or for our benefit to store information and to communicate easy. So quantum communication, we require a mathematical model which can measure spin in various direction and by this mathematical model, if we are able to get the same data also without the error or the error can be nullified. So here your mathematical model plays a very important role. Understood a basic idea of what is the difference between classical computing and quantum? Any doubt till this point? Any doubt? Or should I proceed further?
No doubt, ma'am.
Okay, good. Chaliye. So now next we will discuss with some of the mathematical, some basic, I will just giving an idea. Spin of an electron at various angle. For describing this, we will be using complex numbers because complex numbers will provide an ideal or best way to combine trigonometric and exponential function. So we will be getting, we will be discussing this, how we are representing this. But before this, let's understand or revise this concept vectors. You might have studied this in 12th class very nicely. So vectors normally tell the dimension when we go with the direction because now you are going to tell the inclination or where the electron exists. So it is like a 3D place you are going to tell the direction of the electron's movement. Okay. So for this, vectors are used. Now when you represent vector in vertical, when you list vector vertically, we call them as cats. And when you represent vector as horizontal, we call it as bars. So when I write it like this, it is a cat And when you write it like this, 1 0 pi 23, it is bra. This notations is coming from, I'm just giving you first an idea, then I will go for the qubit notation. First of all, let's understand this notation in a basic form. Paul Dirac has given this notation. It is nothing, it is the vector representation. Vertically you are representing, or you can say in a column form you are representing. It is called as ket. When you are representing in a row form, it is called as bra vector. So what actually it is? Now let's understand initially with a 2D vector. When you are measuring it with this, dimension is this. So suppose the coordinate is 3 and 1, I am representing. So I will be writing it as this. This notation is ket. Got it? Further, it's not compulsory you start by origin only. You can represent like this also. And simply when I represent is this form, it will be. Now the first define the measurement in x direction, and the second define the measurement in y direction. If I say length of vector, I'm going in a bit because concepts are known to you, all of you. So length of this vector, so it is this, all is might be clear to you. So when you are representing in n dimension, you might be writing the vector in ket form as, and more general, the length of this vector is vector of length 1 are termed as unit vector, and qubits are represented by unit vector. Okay, so this is the one thing that you need to remember. Now let's go for some more concepts. Suppose this is a ket vector. If I multiply it with a scalar quantity, a constant value, now my vector will be simply this. You might be have done in the your physics. If you multiply, simply if you multiply the vector by 2, what happens? The vector get expanded or the length expanded, it is simply multiplying. Now suppose you multiply a vector by its bra version. So oh, sorry, I'm just taking one more thing. Before that, let's have a look. Now suppose take a vector, the same one, 3 1. The length of this vector is, now I did, let it be termed as C. Now I have performed C. So what it is? It will be 3 root 10 plus 1 root 10. Let it be termed as, because definitely it will be vector, I define it as ket vector U. Now if I find the length of this ket vector U, it will be, so it is 1. 9 upon 10 plus 1 upon 10, this thing. So simply, so we can simply say in a very simple word, When I multiply the length of the vector with the vector, I will be simply getting a vector u such that this u is a unit vector. The u is a unit vector, and this u is in same direction of ket vector A. Clear? The same concept is there, just I'm making you comfortable with the do terminologies bra and kets which we will use in the qubit notation. So vector addition. This all you might know. Simply if you want to add two vectors, they should be of the same dimension, and the addition is this. So how we represent in the ket form, vector A plus vector B is A plus B. And we all know plus is commutating, so this is also equal to this. Multiplication is not commutative in the vectors, so this will not be commutative here also. Okay. Now next important term in the quantum is orthonormal, orthogonal vectors. Vector A and vector B are perpendicular vector if and only if or simply if you remember, what does this orthogonal theorem says? Pythagoras theorem says when are two vector perpendicular? If I simply say this is vector A, this is vector B, this is vector C. So what is this? Length of length A square plus B square plus C square. We talk about the magnitude in this form. So simple terms. Now if I talk about the dot product, two vectors are orthogonal, or we say perpendicular if dot product is equal to 0. So simply when you expand this thing, normally if you remember, like a square plus, what is a plus b ka whole square? It's a square plus b square plus 2ab. So what I'm saying, I'm saying that a plus b ket square is equal to ket a square plus ket b square. So what it require? It require dot to be 0, which is the condition. Either you write it like this, the magnitude are equal, or the second way of specifying is that the dot product of these two ket vectors are equal. Sorry, the dot product of these two ket vector is equal to 0. Okay. Now let's do one more thing. Now if I multiply a bra vector with a ket vector, so the dimension should be same. This will be this, and this is equal to, you cannot write it in the reverse order, that you can understand also. It's not, that is not possible. Writing this together also, we also call as they are pushed together. Clear? So when I write it like this, the same vector both side, so now it will be equal to a1 square. Presently it is a1 b1 plus a2 b2 plus an bn. So now it will be an square. So simply you can say it is equal to this. And if this is equal to 1, got it? Or simply we say if ket is a unit vector, if and only if is equal to 1, because then the modulus of the length will be 1. Length will be means, that means whole this sum to be 1. Or one more important concept is two vector A and B are orthogonal if and only if this is equal to 0. I will just give you an example to make it more clear. Let's take an example. Your A is vector 3, 1, vector B is 1, 2, and your vector C is -2, 6. When I combine both of them, it will be 3, 1, 1, 2. So it is 3 plus 2, 5. Definitely they are not orthogonal. And suppose I combine A by C, it's 3, 1, -2, 6. So it is -6 plus 6, 0. So this is not equal to 0. So simply it says A and C are orthogonal. So now the question comes, how it works, or how can, let's have a look. Clear? Now suppose if I found so what it will be equal to? It will be, see, this is the vector. Now you want to perform, so it will be a1 plus a2, like the bra form of it, and then it's the ket form. So when you multiply it, you will be getting a1 square plus 2a1 b1 plus b1 square plus a2 square plus 2a2 b2 plus b2 square. Similarly, it is a1 square plus a2 square plus 2a1 b1 plus a2 b2. If I talk about, this is vector A length, this is vector B length, and this is the combination of A and B. For satisfying orthogonal law, we require this should be equal to this. So 2AB is equal to 0. Or in a simple way, when we say, when talk about the vector A and B are orthogonal, when we perform the operation or when we combine them, the result is 0. Is it clear? So I've given you a basic idea of what about vectors and what is the bra and ket notation that we will be using in this qubit. Okay.
Excuse me, ma'am.
Mm-hmm.
Ma'am, it is get vector or wet vector?
Ket.
Ket, K-E-T.
KET.
Okay,
See,
ma'am.
the ket vector you are representing is this form, a column form, and bra is you are representing in the row form. The same vector, how you are representing, if you are writing in a row form, it will talk it as a bra vector, and if you are writing it in a column form, we call it as the same thing. Suppose we are writing the here we are drawing a vector, this thing, this representation we call it as cat, and if I write the same vector in this form, we call the notation as. This is just a notation that means representing instead of row and column. This Dirac scientist represented this in this form, and further, this approach was used in qubit. So qubit used this notation. So to make the you familiar, actually, what is this notation and what this terminology says? That is why I've given you basic examples with just 2D things. Because first of all, I will be giving the examples with 2D, then we'll be moving with the complex numbers and the 3D things. Okay. Any other question? Okay, so we will be taking tomorrow class. The thing is, what are different orthonormal bases? These orthonormal bases are not different. It is simply like you are measuring something and you are taking different scales. Suppose I just told you like this is the same vector which is having the measurement 3 1. So now when I'm measuring with the 0, it is like this. If I'm doing the measurement of this will become 3 1. Just the representation will change. Clear? So the same is the concept, how the different bases will be used, and for different bases how the vectors get transformed. And the same concept we will be using in the qubits also.
Hello, ma'am.
Hmm.
Ma'am, does the multiplication of bra and cat vector is not a vector, ma'am?
It is a vector. The multiplication of,
Bra and cat vectors.
no, it will be a quantity. You just say when you multiply row and column, you get a value now.
Okay, ma'am.
And though it will not be a vector, it will be simply quantity, scalar value. Just see, if I did this thing, here also there was a quantity, and here also we have got a value even given. Clear?
Yes.
Okay. I'm very happy you are students are interacting at least. So the next class we will start with different orthonormal bases, and tomorrow the same time at 2 o'clock. Okay?
Ma'am, please share the slides.
Slides, so I'm not having, I'm writing it on this thing. So if you want, I will be sharing you this what I've written today.
Yes, ma'am.
Ah, I will be sharing. I will be sharing. And after today's class only, I will be sharing. Okay. So we'll meet tomorrow. If you have any doubts, you can ask me later also.